So what do we have today? I figured since I've done a fair bit of work on my Ford with the cooling system in the last couple of months that we would take a look at how an automotive thermostat actually functions. And what we have here is one of the extra ones I have out of the Ford. I believe it's still good. I just hadn't installed it properly because of the weird O-ring that's on this thing in the Ford. You can see it's got, on this one, it's got two different plates. It's got a plate here, which is one stage of it, and then the big one, which is this plug here operated by this mechanism underneath. And that blocks your coolant except for this little air weep hole until the engine heats up, and then this shrinks down, backs off, and opens. This, I believe, is a secondary circuit to kind of allow a little bit of recirculation for some other reason. I'm not quite sure why. Could be they want to take a little less chance of the thing completely blocking up if it does fail close, because this is an aluminum engine. I'm not sure. But anyway, so what you've typically got in here is this copper looking canister. Inside of that is a wax, a very specifically formulated wax that at whatever temperature this thing is rated for, it melts. And when it melts, I'm thinking that it changes volume significantly versus when it's solid. So when it's solid, the volume increases, and when it melts, the volume decreases. And if that volume decreases, this spring allows this to compress. And being a sealed system with no leaks in there, it can't displace any air, so the only thing that's setting this pressure up on this is whether or not this thing can actually, the change in volume of this material that's inside of this pocket here. So as that changes, then it allows this to, the dimensions to change, which is attached to this plunger, and then it is able to pull down against the spring. And then as the spring to stabilize it, that spring is a little bit strong, but it's not too bad, but then the spring stabilizes it when it returns and makes sure it has a good tight shutoff. So what we're going to do now is we're going to heat up some water to, I think this is a 192, I think. We're going to heat up some water and then throw this in there and watch what happens. This will also apparently be an experiment to see whether a watch pot actually boils. Interesting. So we'll give it some steep time at this temperature before we turn it back on and turn it up. Even though it's a little bit of metal in there, it should be pretty close to the water temperature at this point, since it's been in there basically the whole time. But it has not moved. Alright, turn that back on. See where it does open. You can see that it has opened now. And what we're going to do is we're going to let it sit and watch when it closes. Because it could be that again, the hysteresis of the material, it took it a little while to actually get to its opening temperature, and now we have surpassed it. So that's a good possibility. So we're going to watch this for a little while longer and see what temperature it closes at. See if it closes at close to 190. As you can see at this point, it's modulating at about 197 degrees. So this is where you would probably normally see the thing as it was running in your car. And it's never going to be fully open like we had a minute ago, but it shouldn't be fully closed either. It's going to be back and forth letting flow through in order to keep itself at whatever temperature it's set at, which I believe, as we're getting close here, does appear to be about a 192. As you can see, it's slowly closing. And at 192, it is effectively closed. So it is a 192. It took it a little while to fully heat the center in order for it to melt and allow it to pull back on that spring. And then at 192, it is fully seated again. So what we're going to do is we're going to let this cool down to ambient, and then I'm going to take it out into the shop and cut it apart and see what's in it. So here we are in the shop. There doesn't appear to be too much holding this thing together. I don't know if you can see that on each side there you've got this little rectangular piece that doesn't look quite right. Well, that is the center of, I don't know, the girdle, I guess, that holds that whole spring together. We're going to go get a little death wheel, do a little quick work on that, and see if we can shoot this thing across the room. So apparently that's not just pressed in, it's welded. So we're going to try to get a little bit more brutal with it. See if we can get her apart without completely screwing up everything else. There it is. That side is out. And grinding it did help. So we're going to hit that again. And there it is. She is out. And what we have is the centering pin, looks like on a little ball up in here, just to make sure that as she moves up and down, it stays sealed. And I'll have to say, I don't know whether there's an O-ring in there or not, but that holds pressure. Interesting. So what we have now, since that's been released, is this outer spring really springing and pushing that. So we're going to cut that and move on. It's like lowering a Honda. There we go. Alright, so see if we can get that spring out of there. May have to cut it in a few more spots, so as it's kind of coiled up there, but yeah, so that is a compression spring, and the bottom one is still decent. So I'm going to pull that spring off. Be right back. Alright, so the spring is off, and it's a little stouter than I expected. So now we're going to cut this piece off. I don't think you need to necessarily see that because there's nothing terribly interesting there, but we'll do that and be right back. So that piece is now off. I actually managed to cut it without touching what appears to be copper. So the only thing left on this thing is this bottom piece, which isn't too consequential because it's just a standard compression spring. It's held on by a little swedge lip on the bottom of that. The numbers in there. 120. I don't know what that means. Anyway, so now the fun part is going to be seeing how we can get this apart. If I'm going to have to cut it, or maybe I can twist it, we're going to see. I'm going to go get another pair of pliers and start with a little twist. So this whole top piece appears to be crimped on as far as the sealing surface goes. So that whole thing would move away like that on that pin. Yep, there's something that moved. Oh, okay. Those are just pressed on. All right. Not sure if I'm going to be able to do anything with that, but now we're down to the actual insert piece here and the bottom cup. Does not seem to want to move, even though that is what shrinks into there. So there is something in there holding this together, and I am not sure exactly what that would be. So we are going to start cutting along here and see what happens. Maybe we're going to have to cut along both sides and go from there. But because of that, I think the first thing I'm going to do is take this bottom piece off, which isn't going to be, well, we'll see. I don't know. I don't know how interesting this is going to be. I don't think I'm going to be able to crush that and get it off. I'm going to have to cut it. So we're going to start cutting. I'm going to cut down through here and then peel this off. Alright, so those pieces came off pretty easy along with the other spring. Nothing too special there. So now we're going to try, see what we can do. We're going to cool it off for a second while the air compressor is running. We're back. Let's try to hit the other side. Cool it off a little bit, but not quite through yet. Cool it down a little bit again. Alright, so that is strictly an outer sheath. This is actually the pellet. So what moves is this piece. Well, I guess we'll keep cutting. Pretty stout. And you can actually start seeing some of the wax that's in there. Pull it off again. There it is. All right. I may have had this whole thing backwards. That's material. This outer layer here, that's the wax. And what it appears to do, very interestingly, is this is a rubber grommet, and it actually expands as it heats up and squeezes this in this manner to push that spring. So this waxy stuff that looks kind of bronzy, that is actually what, as it heats, expands, closes in on this rubber membrane and pushes up on this pin. So if any of these parts fail, over time, if it wears a hole in this rubber membrane, or somehow, I don't think you'd scuff through this. You can see this copper is pretty thick. Bronze or whatever that is. It's pretty thick. I don't figure that was normally what fails. It's probably what fails is this. Or the spring. But anyway, so those are the insides of your average automotive thermostat. It's pretty simple and fairly ingenious, and I would assume that manufacturing this wax or melting material so that it is a very, very quick melt at the specific temperature, and then setting it up so that it expands a certain amount as it gets up to that temperature so that it can push down on this with enough force to compress that spring. That spring was pretty stout, but there you go. Not much left of it, but for $5, why not? That is how a thermostat works in your car. So I appreciate you all watching. If you're interested in any of the tools that I use to commit this butchery, they'll be linked in my Amazon affiliates page. Otherwise, y'all take care. Talk to you later.